Now we're going to look at yet another way to define the power of a point if the point is outside of the circle. Suppose this is point A and this is circle K, and I'm looking for a way to define the power of A with respect to the circle K. Well, one way is to draw a line through A that intersects K at points, say, B and C, and then to just write AB times AC. But now think what would happen if I took the points B and C here, such that B and C get closer and closer together. Then AB and AC would get approximately the same. And the limiting case is when I get the tangent line to the circle when B and C would coincide. So here I took a tangent AT such that T lies on the circle. Then our assumption is that the power of A with respect to the circle K can be expressed as AT times AT, or AT squared. Let's see if that's the case. I'm going to connect this segment and this segment, and now I'm going to use the alternate segments theorem, which tells us that this angle equals this angle because they both correspond to this arc. Aha! Now we see the similar triangles. Triangle ATB is similar to triangle ACT because this angle equals this angle, and this angle is common in both triangles. Similar triangles have proportional sides, and so AT divided by AC equals AB divided by AT. Note that AT first we considered with respect to this triangle as the side against this angle here, and then we considered with respect to this triangle, but as the side opposite to this angle. We get AT squared equals AB times AC. And now this equation confirms that the power of A with respect to K is not only AB times AC, but can also be written as AT squared, because AT squared equals AB times AC, which is the power. Now let's try to prove that if we take two lines and choose 2 points on one line and 1 point on the other, such that if this is x and this is y and this is z, and we have that x squared equals y times y plus z, so x squared equals y times y plus z. Let's prove that the circumcircle of this triangle is actually tangent to this line. Well, let's assume that's not the case. Let's assume it's not tangent, and it intersects this line again at this point. I'm going to prove that this point and this point coincide, meaning that this line and this circle only have one intersection point, which means that this would be a tangent line. Let's call this segment T, and then we have, from the power of this point with respect to this circle, we get these two equations, and we can subtract one from the other. So this x squared will cancel out with this x squared, and this y times y plus z will cancel out with this y times y plus z. And the only thing that will remain is x times t. So x times t equals 0, so either x is 0 or t is 0, but x cannot be 0 since that's how we defined x to be some positive length, and therefore t equals 0. And so this circle must be tangent to this line. Here's the optional problem. We start with an obtuse angled triangle here, with this angle is obtuse. This is its circumcircle. Then this here is a tangent line at this vertex of the triangle to the circumcircle, and it intersects the side of the triangle here at this blue point. This point is defined as the reflection of this point with respect to this blue point here. So this equals this, or the blue point is the midpoint of the segment between this and this point. This point is defined as the reflection of this point with respect to this line, the tangent line. So this is perpendicular to this, and this equals this. We have to prove that this quadrilateral is cyclic. And here's the solution. First of all, from the alternate segments theorem, we have that this angle corresponds to this arc, which corresponds to this angle, and so this angle equals this angle. Next, because of this symmetry, we have that this triangle here is isosceles, and so this median and altitude is also an angle bisector, and so this angle equals this angle. Similarly, this triangle here is also isosceles, and so this angle equals this angle. Now, let this distance be x, and this distance be x, the distance to this blue point. And let this distance here be y, and this be z. We know that this is tangent to the circle, and this is a line that intersects the circle at 2 points, and therefore, from the power of this point with respect to this circle, we have that x squared equals y times y plus z. And therefore, x squared looked from here equals y times y plus z, which means that the circumcircle of this triangle is tangent to this line at this point. And now, from the alternate segments theorem, we have that this angle corresponds to this arc, and so it equals this angle. Now, if this angle is alpha and this angle is beta, then this angle is alpha and this angle is alpha, and this angle is beta and this angle is beta. We've already proven that. Then, this angle here must be 180 minus alpha minus beta because of the sum of the angles in this triangle. But this works perfectly, because now this quadrilateral is cyclic, since this angle is alpha plus beta, and this angle is 180 minus alpha minus beta, so their sum is 180 degrees. And we're done.